Welcome back. We are going to talk about solving systems of linear equations using matrices. So in an earlier section we talked about how to solve systems either using the graphing method, the substitution method, or the addition, sometimes books call it the elimination method. So those were three ways. Now we're going to talk about how to do it using what are called matrices. Okay, to write an augmented matrix. The process. The augmented matrix associated with the linear system ax plus by equals c and dx plus ey equals f is formed by writing only the coefficients of the variables and the constants as follows. You're going to write the matrix A, B, C, and then the second row will be D, E, F. Now I do want you to notice that they put this little bar, this vertical bar, where you would normally put the equal sign. Alright, so an example. Write the augmented matrix for the system 3x minus y equals 10 and 5y equals 12. So the matrix will be 3, negative 1, 10, and then row 2, there's no x term. So we're going to have a 0 as a placeholder in the matrix. 0, 5, 12. All right, for number 2, it's not in the right form. They're going to make us work for it. So here for 2x plus 3x plus y equals 1, we need to get that in standard form. 2x plus 3x plus 3y equals 1. Collecting like terms, 2x plus 3x is 5x plus 3y equals 1. All right, now for the second equation. I have 14 equals 6 times x minus y. Distributing the 6, 14 equals 6x minus 6y. So my system is actually 5x plus 3y equals 1 and 6x minus 6y equals 14. So my augmented matrix will be row 1 is 5, 3, 1, and row 2 will be 6, negative 6, 14. So what should you have? What's the take-home message for example number 2? You have to put it in standard form first before you can write the augmented matrix. Let's look at number 3. X plus z equals negative 1. 2x plus y equals 5. Negative y plus z equals 3. Okay, a couple things to notice. You now have 3 equations, so your matrix will have 3 rows. And you also have 3 variables. That first equation, I have 1x. I don't have any y, so I've got to put a 0 where the y would go, plus 1z equals negative 1. For equation number 2, I have 2x plus 1y plus no z's, don't forget the placeholder, equals 5. And then for the last equation, I don't have any x's, so 0x minus 1y plus 1z equals 3. Hopefully you got that. Don't forget about the placeholders. Okay, for the next example, write a system of linear equations represented by the augmented matrix. And now we're going to go backwards. Let's read off line number 1. Negative 8x plus 7y equals 113. 2x plus 0y, I don't have to write that because that's kind of understood, equals 1/3. There's my system. For number 5, write the corresponding system. I notice I have 3 equations, and I'm going to have 3 variables, x, y, and z. So this first line says that x equals -3. The second line says y equals 0.05. And the third line says z equals 12. Wouldn't it be convenient, because this gives me the solution to that system? So, something to notice. You have 1s going down the diagonal, and you have 0s above and below all those 1s. You're going to see that again. Okay, the next topic is to use elementary row operations. And I'm really kind of going over this for those of you who may be going on to be a business major, and you're going to have to take Math 1324, which is mathematics for business and social sciences. You're going to see something called, these row operations on matrices when you do a unit on what's called the simplex method. So I do want to go ahead and introduce the row operations, even though I won't be testing on it in this class. All right, operations that produce row equivalent matrices. An augmented matrix, so those are the matrices we just created, is transformed into a row equivalent matrix by performing any of the following row operations. Again, you could interchange 2 rows. So you could say like row 1 is interchanged with row 2. Or you can do a row is multiplied by a non-zero constant, right here. Or a constant multiple of one row is added to another row. So let's go do some examples. Perform the given row operation. Row 1 is interchanged with row 2. So here's your matrix. When you do that row operation, what do you get? All right, row 1 becomes row 2. So 6, 3, 0 is row 2. And row 2 must become row 1. 1, -2, -12. That's it. You just did this row operation. Let's do another example. Row 1 interchanges with row 3. So when you do that row operation, what do you get? Row 1 becomes row 3. So 3, 6, -8, -7 is row 3. Row 3 becomes row 1. 1, -2, 7, 8. You don't do anything to row 2. Leave it alone. That's it. Number 3. The row operation tells you to do 3 times row 1 and make that your new row 1. Okay, 3 times row 1. Row 1, I want to multiply everything by 3. I would get -6, 12, -18. It did not tell me to do anything to row 2, so I'm going to leave it alone. 6, 3, -12. All right, the third row operation, the third type, -2 times row 1, add it to row 2, and that becomes your new row 2. Okay, so I'm going to take row 1 and multiply it by -2. I'm going to come down here first. So I get -2, -6, -12. I want to add that here to row 2. So row 2 looks like that. I want to add them. I get 0, -2, negative 13. Now, once I do that, that becomes my new row 2. So 0, negative 2, negative 13. That's my new row 2. Now, even though it told me to do something to row 1, at the end of the day, the only thing that changed was row 2. So I'm going to keep my original row 1. Okay, why in the world do we need to know how to do row operations? It's so that we can manipulate matrices into what are called reduced row echelon form. So in short, reduced row echelon form is RREF. A matrix is in reduced row echelon form if any all 0 rows are at the bottom of the matrix. Look at number 3 down here. See the row of all zeros? It's at the bottom. For all other rows, the first non-zero entry is 1. So the first non-zero is a 1. The first non-zero in this row is a 1. First non-zero is a 1, 0. First non-zero is a 1, 0, 0. First non-zero is a 1, and so on. Number 3, the leading 1 in each non-zero row is to the right of the leading 1 in the row immediately above. What does that mean? That means that you have to have 1s going down a diagonal. Okay? Each row with a leading entry of 1 has zeros above and below the leading 1. Now, why is that handy? Remember up above we said we could read off x equals negative 7, y equals 15, and z equals 12, and you'd have the answer to that system. What's the answer to the system here? You get x equals negative 27 and y equals 6. All right, so a summary. Possible final matrix forms for a system of 2 linear equations and 2 variables. You can have exactly one solution when you have your 1s down the diagonal, your x equals m, y equals n. If you have a row of all zeros, there are infinitely many solutions. And then if you have 0 equals something other than 0, there's no solution. Some examples. This is where your calculator comes in. All right. And actually, I want to do it this way so I can see the system. All right, you are going to go push. Follow me on the button pushing. You're going to do matrix, so it's above the x to the negative 1. You're going to hit second matrix. You're going to arrow to the right to edit and hit enter. There will be 3 rows and 4 columns. It's a size 3 by 4 matrix. And you're going to go type in these coefficients. Okay, so you're going to have 2, enter, 7, enter, 1, enter, 14, 1, 3, negative 1, 2, 1, 7, 12, 45. Once you have all of the coefficients entered, hit second quit. All right, we're going to go look at that matrix. So hit second matrix and just hit enter because you should have entered it as matrix A. If you hit enter, you should see that matrix. Okay, now you want to do RREF. So I'm going to go to second matrix. It's a mathematical operation on a matrix, so you need to arrow to the right. And you can either arrow up, or if you arrow down, you've got to arrow down quite a ways. You've got to go down to letter B. RREF. Don't do REF, make sure you do RREF. Hit enter. Now you want to do RREF on matrix A. Oops. RREF on second matrix A. You can close the parentheses if you want to, and hit enter. That's in row reduced echelon form, so my answer is x equals 2, y equals 1, z equals 3. If you wanted to do the ordered triple 2, 1, 3, that's fine too. All right, example number 2. So isn't this a much faster way? You can go graph these. Well, you can't. You don't even know how to graph planes. But if it were 2 equations and 2 unknowns, you could graph them. You could do the substitution method. You could do the addition elimination method. Or you just go jump over on your calculator and use your matrix. Okay, second matrix. Edit. Enter. It's a 3 by 4. 2, 7, 11, 11, 1, 2, 8, 14, 1, 3, 6, 8. I'm going to make sure that's all correct. Looks good to me. Second quit. Second matrix math. RREF. Enter. Second matrix A. Close parenthesis. Enter. The answer to this system is the ordered triple 14, -4, 1. Number 3. Second matrix. Edit. It's a 3 by 4. The matrix is 3, 5, -1, -2, 4, -1, 2, 1, -6, -10, 2, 0. Second quit. Second matrix. Make sure it's right. Uh-oh. I'm off. Big time. Well, second matrix. Edit. 3. Enter. 5, -1, -2. 4, -1, 2, 1, -6, -10, 2, 0. Always make sure to check. And I am kind of running through it fast, kind of on purpose, but also to show you how easy it is to make mistakes. So make sure you check it. Second quit, second matrix, look at it, we're good to go. All right, second matrix math, RREF, second matrix A, enter. Ew, yuck. But notice this last row, I have 0, 0, 0, 1. So just to make sure you see what I'm seeing on that last row, right here. You can't do that. 0 does not equal 1. So the answer is that there's no solution. All right, number 4. Second matrix, edit. Ooh, I see x's and y's and only 2 equations. So I've got 2 rows, 3 columns. So I have 4, -1, 9, -8, 2, -18. Second quit, second matrix A. Looks correct. Second matrix math, RREF. Second matrix A. Uh-oh. Look at this one. I have a row of all zeros. So the answer, you have infinitely many solutions. All right, to go above and beyond, I have 1 negative 1/4 and 2 1/4, which is what's that, 9/4? And then 0, 0, 0. Okay, that first row says x minus 1/4 y equals 9/4. So if I add 1/4 y to each side, I get x equals 1/4 y plus 9/4. So my answer is going to be 1/4 y plus 9/4, comma, y. There are infinitely many points that satisfy that condition. Y can be anything, and as long as you know y, you can go get x. But what I want you to notice is if you have all zeros at the bottom, there's infinitely many solutions. All right, last problem. Second matrix, edit. It's a 3 by 4. 2, oh no, 3 enter, by 4 enter. Okay, 2, 1, negative 3, 0, 4, 2, negative 6, 0, 1, negative 1, 1, 0. Second matrix, let's look at it. Good. Second matrix, math, RREF, matrix A. Oh boy, I see a bunch of zeros at the bottom again. So there are infinitely many solutions. Now if you had to go find out what those solutions are, I'm going to do math frac to get fractions, so it's not yucky decimals. 1, 0, 0, 0, 1, 0, negative 2/3, negative 5/3, 0, 0, 0, 0. All right, this gave it away that there's infinitely many solutions. What form do those solutions have? This tells me that x minus 2/3 z equals 0. So x is going to equal 2/3 z. This one tells me that y minus 5/3 z equals 0. So y equals 5/3 z. So my answer, if I wanted to tell you what form those coordinates, what do they look like, I would get 2/3 z for x, 5/3 z for y, and z could be anything. That's it. This should be very helpful to those who are going on to Math 1324 for a business degree. All right, take care.